ICMR, Odisha State Higher Education Council, Sambalpur University, and Zimbabwe. He has published more than 40 research papers in reputed journals and conferences. He is also a senior member of IEEE and presently working on deep learning models. His areas of research include swarm algorithms, machine learning, deep learning, time series forecasting, and soft computing, seamlessly centered around our events theme, that is, recent advances in the field of artificial intelligence and machine learning. He has delivered more than 10 technical talks in seminars, webinars, and workshops in institutions of national importance. We extend our heartfelt gratitude to Professor Sibarama Panigrahi sir for gracing our event with his esteemed presence. Now, without further ado, let's welcome him on the stage to enrich and inspire us with his valuable insights on the topic Advances in Neural Network and Deep Learning. Please, sir.
Thank you very much for the nice introduction. So today's talk is on advances in neural network and deep learning. But before starting the talk, let me tell you one thing clearly. Every artificial thing can be modeled from a real life thing. For example, aeroplane has been modeled from the flying of birds, right? Camera has been modeled from our eyes, right? Similarly, computer, if I am not wrong, computer is a duplicate copy of human being. It means what we are having, computer is having a copy of that. Okay, so broadly speaking, computer has two components, hardware and software. Similarly, we also have two components, hardware and software, right? So you see our physical components, hand, eye, ear, nose, these are the hardware components. Whereas mathematics, your enabling of eye, enabling of mouth, the software which enables the hardware components, and the application softwares like Korea, Hindi, English, these are also installed in us. So those are the software components, right? So the hardware components in us, there are basically 5 hardware components: input devices, output devices, memory devices. So we have memory devices, we have arithmetic and logic unit, we have control unit. Similar to us, computer also has those things. So why I am telling you all these things? Because you see, today's talk is on neural network and deep learning. So here we will mimic how a biological nervous system or how our brain works, right? So I will go mathematically because it is a combination of mathematics and computer science. I will go both mathematically and through a programming point of view. I will try to mix both the things so both the students can get a flavor of it. So in this talk, I will start with the introduction to neural network. Then I will go through the mathematical model for neural network. Then differentiation and its application in or to train the neural networks. Then I will go through the deep neural network. Then the recent advances in deep learning, that is recent activation functions, weight initialization schemes, dropout regularization, batch normalization, and recent optimizers like Atom. Then how to build and train a deep neural network. Then if time permits, I will tell you how you can optimize the hyperparameters of a deep neural network. So let us first go through what exactly a neural network is. So a neural network or an artificial neural network is a mathematical model that simulates the structure and functionality of biological nervous system. So as it simulates the structure and functionality of biological nervous system, before going to artificial neural network, let me ask you one question. What will happen to you if a mosquito bites you? Yes, you will. If a mosquito bites you, what you will do? Suppose a mosquito is biting to your left hand, what do you do? Very good. Please sit down. So you see, a mosquito is biting to you. It means a stimuli is generated on the left hand. Then based on your experience and based on the type of feeling you are getting, your brain decides that yes, it is a mosquito, and it responds to the other hand that go and kill the mosquito. Right? So if you are not so experienced, the brain may also ask the eye, go and see what is happening on the left hand. Then the eye will see a mosquito is biting. It will send an instruction to the brain, a mosquito is biting. The mosquito will take the decision and it will instruct the other hand to go and kill the mosquito. So our nervous system is basically having two things. One is receptors, that is the organs which receives the input signals. Next one is neural network or brain, which processes the input signals and takes a decision. And it gives the instructions to the effector organs, the other hand, which goes and kills the mosquito. So this is what we are doing in a biological nervous system. So let us see how we will mimic it. So in order to understand it, let us go deep into neural network, okay, or the brain. So a biological nervous system or the biological neural network consists of some millions of neurons with trillions of interconnections among them. So what is a neuron? Neuron is the basic processing element of our brain. So in our brain, there are some millions of neurons which are interconnected with each other. Right? So if I will go into a single neuron has three components. One is dendrite, which receives the input signals. Am I audible to all of you? Yes. So you see the dendrites. Dendrites receive the input signals and the net weighted summation of input signals goes to the cell body. It takes a decision and based on that it produces an output through the axon. So now this dendrites may be of two types. One is apical dendrite, another one is basal dendrite. So basal dendrite means what? The basal dendrites receive the inputs from the receptive zone, whereas apical dendrites receive the input which is an output of another neuron because the neurons are interconnected with each other, right? So output of one neuron is fed as the input of another neuron, and such kind of inputs are accepted through apical dendrite, right? So now let us go through it how we will mathematically model it, right? So now you see. Can you see there might be n number of inputs? So you see you are listening to my lecture. While listening to my lecture, you might be thinking something else. A mosquito might be biting to you, an ant might be biting to you. So you see various kinds of inputs are going to you. And every input is associated with an weight or importance. So if you are giving importance to my lecture or my input, then you might not feel that a mosquito is biting to you. But if you are not giving importance to what I am talking and a mosquito is biting to you, so you might know that a mosquito is biting to you and you can take the actions accordingly. So here the important thing is every input is associated with some weight. Okay, and then what we are doing, we are taking the or making the weighted summation of inputs, right? So then, so whatever input you are getting, weighted summation of inputs, based on the weighted summation of inputs, you are giving an output response. For example, a mosquito is biting to you. Okay, so that is one input to your brain. So are you biting the mosquito? No. Your other hand goes and kills that mosquito. Means based on the weighted summation of inputs, you are providing an output response, right? And in order to provide the output response for a particular and artificial neuron. So let me take a case neuron. This neuron may have n number of inputs. Each input is associated with some weights. And here I am adding another weight that is a bias component. Why I am adding a bias component, I will explain it to you mathematically. Right? So next, what we are computing? We are computing the weighted summation of inputs. So the net weighted summation is nothing but W1 into X1, W2 into X2, dot 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 Wn into X1 plus the bias component. Right? So why I am adding the bias, I will tell you. Please wait. So next we are passing the weighted summation of input to the expression function to get the output response. So yk is nothing but f of vk. Okay. So now why we are using a bias component, or what we are trying to do through a neural network which is a collection of millions of neurons with trillions of interconnections. Let us go deep into this. Right? So for that, let me simplify it. Let me take a single neuron with a single input. Okay? So this input x1 is multiplied with the weight component w, and the bias, we are adding the bias component b. Next, we are computing the output. Let us consider that we are using a linear activation function. Linear activation function purely is an activation function which gives the output what it takes as the input. Okay, so yk is nothing but f of bk. So the whatever the input bk will be, the same thing will be the output. So w into x1 plus bk. Right. So now what we are doing over here, you are always doing these things, or you have already done these things in mathematics. So let me show you what you have done. So in 10th or 11th standard, what you have done a data fitting application. Suppose you want to predict the weight of a person based on the height, right? Is there any mathematical formula? Or is there 11th standard, right? Next, after that, if I want to predict my weight, I will give my input as my height. Let's say my height is 5 foot 5 inch. So in 5 foot 5 inch, I will give the input. I will make it to the corresponding line. Then I will get the corresponding weight. Let's say 70 kg. Yes. So what I am doing over here, I am not doing anything else. I am with black point. You see, there is an error. Our fitted value is this, whereas our actual value is this. Right? So here you see, here the red point, here our fitted value is this, fitted value is this, whereas actual value is this. So there is some error. So how you are computing the error? Actual value minus fitted value. But if you will do actual value minus fitted value, there might be some positive errors and there might be some negative errors. So the positive errors and negative errors